Welcome to lecture 28, where we explore the Taylor formula centered in a generic point x0. This is nothing else than an extension of what we said in lecture 27, where we present the Taylor formula centered in the origin. Now we are taking a generic point x0. Let me change the dimension of this pen. So let's say that x0 is a generic point on the real line, and we have a function f that is defined in a neighborhood around x0, x0 minus r, x0 plus r, that takes value into real line, where r is any real number larger than 0. Okay, and let also suppose that n is the usual natural numbers without the 0. Okay, so if the following two conditions are verified, so first condition, f has the first n minus 1 derivatives in the interval x0 minus r, x0 plus r. So we are asking now that if let's say that this is the real line and we have x0 minus r here, x0 plus r here, and we are asking that the function f has n minus 1 derivatives in the entire open interval that goes from x0 minus r to x0 plus r. The second condition is that f has the first n derivatives only in x0. So the second condition is asking something different, is asking that n derivatives, the first n derivatives, are defined exactly at the point x0 that will be somewhere here. Okay, now if these two conditions are verified, then we can say, let me move this here, then we can say that for every x that belongs to the interval x0 minus r, x0 plus r, we have the following expansion. So we can say that f of x for every possible x that we can pick in this interval, let me use a different color here. Let's say, for example, this x, well, for that x, f can be expanded into a new polynomial, sum. K goes from 0 to n of f k, kth derivative, evaluated this time at the point x0, divided by k factorial, all this multiplied by x minus x0, all raised to the k, plus little o of what? Well, of the difference, x minus x0, all raised to the n. And this, of course, is valid for x that goes to x0. Now, what we have just given, this is the Taylor's formula with center x0. It is nothing else than a new version of the Taylor formula that we presented in lecture 27. The only difference is that now the function is expanded around a new point x0. Now there is an alternative expression of this. We can say, or equivalently, by setting h equal to x minus x0, which implies, of course, that x is just equal to x0 plus x plus h. And let me represent this. We're saying that we have x0 here. This is x0 minus r. This is x0 plus r. And we're picking now a point x, okay, any point x that belongs to this open interval can also be represented by just an increment h, that is the distance of x from the center x0. Now if we use this h, we can write that x, f of x becomes f of x0 plus h, which is now equal to the sum. K goes from 0 to n of the kth derivative evaluated now at x0 divided by k factorial. And instead of having x minus x0, we can just write h raised to the k plus little o of h to the n. Okay, and this is for h that goes to 0. This is just an equivalent representation of the same idea, expanding the function at a generic point x0. It is worth noticing that if we put n equal 1, the previous formula gives f of x0 plus h equal to, well, we have only two terms in the sum, okay? We have the term for k equals 0, which will be basically f of order 0 evaluated at x0 divided by 1 factorial h to the 0. The second term for k equal 1 will be f of order 1 evaluated at x0 divided by this was 0 factorial, and in this case is 1 factorial, h to the 1 plus little o of h to the 1, which is, of course, this can be rewritten as f of x0 plus h equal to, remember that 0 factorial, just like 1 factorial, just 1, and the derivative of order 0 is nothing else than the function itself evaluated at x0 times h to the 0 is just 1, plus we have the first derivative evaluated at x0 times h plus little o of h for h that goes to 0. But this is nothing else than the expression of the differential. We recognize this to be exactly alpha, the differential. So we can write down observation which is the following. The differential is nothing else than the Taylor formula for n equal 1. Now I will provide now a derivation of the Taylor formula centered at the generic point x naught from the formula that we presented last time of the Taylor formula centered at the origin. Okay, so by just setting f of x naught plus h, notice that the argument of f is x naught plus h, but only h is a variable, right? So x naught is just a given number. So we can consider this to be a new function g of the only variable h. Okay, the same way we see that if we take the kth derivative of f evaluated at x naught, this is nothing else that the kth derivative of g evaluated at 0. In fact, taking the kth derivative of f at x naught means that we are assuming h to be equal to 0. So this is equal to the kth derivative of g evaluated at 0. And now we can expand this function g of h by using the Taylor formula centered at the origin. This becomes sum k goes from 0 to n of the kth derivative evaluated at 0 divided by k factorial times h to the k plus little o of h to the n. But with the previous positions, this gives sum k goes from 0 to n. Instead of g, the k derivative of g at 0, we'll just replace f, the k derivative of f evaluated at x naught divided by k factorial, and instead of h, we just replace x minus x naught raised to the k plus little o of, instead of h, we have x minus x naught raised to the n, and of course this is valid for x that goes to x0. And this concludes the proof. Now that we know how to pass from the Taylor formula centered in x naught to the Taylor formula at x equals 0 at the origin, we can consider from now on, just for simplicity, the Taylor formula centered at 0. And what we want to show now is we want to illustrate some algebraic properties of the Taylor polynomials centered in x naught equals 0. Okay, so this is what we're gonna do now. And let's start with the first one is the sum. Okay, we want to establish the sum of Taylor polynomials. So let's say, for example, that we have f of x that can be expanded into a polynomial Pn of x plus little o of x to the n. And then we have another function g of x that is expanded into another Taylor polynomial of order n, Qn of x plus little o of x to the n. Now we want to prove this property, that the function which is the sum of f of x and g of x, this can be expanded now into Pn of x plus Qn of x plus little o of x to the n. Okay, so this is the formula that we want to prove. And we will provide two proofs of this. Okay, so the first one is based just on the definition of the derivative of a sum. Okay, so if we take the kth derivative f in 0 plus the kth derivative of g in 0, well, these, because of the theorems about derivatives, is nothing else that the kth derivative of the function f plus g evaluated at 0, right? So when we try to expand f plus g evaluated at x, well, this, by just applying the definition of Taylor polynomial, is going to be the sum for k that goes from 0 to n of f plus g, derivative of order k evaluated at 0, divided by k factorial, times x to the k plus little o of x to the n. And now, by replacing the expression of the derivative, we have sum k goes from 0 to n of f, the k derivative of f in 0, divided by k factorial, x to the k, plus the sum k goes from 0 to n of g, derivative order k evaluated at 0 over k factorial times x to the k, plus little o of x to the n. Well, actually, we would have another little o of x to the n, okay, that comes from the expression for the first derivative, but this is just like saying that this is Pn of x, right? So you see that this is Pn of x plus, well, this is Qn of x plus little o of x to the n. And this will conclude the first proof. We have another proof of this. Proof 2. This second proof is even simpler, okay? Because we can immediately write f of x plus g of x and just replace to f of x Pn of x plus little o of x to the n, to g of x Qn of x plus little o of x to the n. And because of the properties of the little o, we know that this is Pn of x plus Qn of x plus little o of x to the n, which concludes the proof. Okay. Right, so second property, multiplication by a constant. So let's say that we have f of x given by Pn of x plus little o of x to the n, and we have a, which is any real number, and of course let's exclude the 0 just because otherwise it will become trivial. We want to prove that this implies that the new function obtained by multiplying a times Pn of x will have an expansion which is a times, this is a f of x will have an expansion which is a times Pn of x plus little o of x to the n. So this is the thing we want to prove. Okay, so let's give proof, which is quite straightforward, I would say. If we multiply the given f of x by a, what we get is a f of x equal to a times Pn of x plus a times little o of x to the n. But this is nothing else than a times Pn of x plus little o of x to the n, which concludes the proof. Now, If you don't believe that this is true, so if you doubt that a times little o of x to the n is indeed little o of x to the n, we can give the proof of this, okay? If we write little a of o of x to the n, right? So we have the, remember that little o of x to the n is a function which can be expressed as omega x times x to the n, where omega x is a function that goes to 0, right? So, but we can now pick basically these elements and we can call this omega 1 of x, and we see that this is clearly something that goes to 0. Now that implies that little a of little o of x to the n can be expressed as omega 1 of x times x to the n, with omega 1 of x that goes to 0. But this means that this is nothing else than little o of x to the n. And this will conclude the second proof. Let's now see what happens if we consider the product of two functions. So f of x can be expanded into Pn of x plus little o of x to the n. G of x is expanded into Qn of x plus little o of x to the n. And we are saying that the product P of x, which is basically f of x times g of x, well, this is now expanded into Pn of x Qn of x, which is basically the product of the two Taylor polynomials, plus little o of x to the n. Now notice that in this formula, this product Pn times Qn contains only terms with degree less than or equal to n. So let me give you an example. Let's suppose that we want to expand the polynomial up to degree 4. Okay, so we have f of x equal to p4 of x plus little o of x to the 4, g of x equal to q4 of x plus little o of x to the 4. When we multiply Pn and Qn, we may end up with terms up to the degree 8, right? Because we may have a term x to the 4 in Pn, a term x to the 4 in Qn. If we multiply them out, we get x to the 8. However, these will be consumed, will be encapsulated by the little o of x to the 4 in that case, okay? So basically in this formula we need to specify that what is left, okay, in the product of the two polynomials are only terms up to the degree n, okay? So all the other terms are basically eaten by the little o of x to the n. Okay, so now let's give a proof of this statement. And well, the proof is quite straightforward. We just take p of x and we multiply out the two Taylor expansions. So we have f of x, which is Pn of x plus little o of x to the n. And for g of x, we write Qn of x plus little o of x to the n. Okay, and if we multiply, we get Pn of x times Qn of x plus we have Pn of x little o of x to the n plus Qn of x little o of x to the n plus little o of x to the n times little o of x to the n. Now, it turns out that all these three terms are indeed little o of x to the n, which lead us to conclude that this is Pn of x Qn of x plus little o of x to the n. Now, you might still have a doubt that these three terms are indeed little o of x to the n. Let's pick one of them, okay, because the other proofs are totally similar to this. Let's say, for example, that we want to prove that Pn of x times little o of x to the n is indeed little o of x to the n, okay? Well, we know that little o of x to the n can be expressed as omega of x times x to the n. This is just a definition, right, of little o of x to the n. And let me rename this product, okay? Let me rename, or let me write this these ways, okay? Well, we can just rename this product of these two terms omega 1 of x. Now, I want to prove that omega 1 of x tends to 0 when x goes to 0, right? So let's say, well, omega 1 of x, what is the limit when x goes to 0 of omega 1 of x? Well, omega 1 of x is the product of a continuous function, Pn of x. This is just a polynomial, so it is continuous. So this becomes basically Pn of 0. Let's apply this theorem of the product to an example. Okay, let's consider the function f of x equal to the sine of x times the logarithm of 1 plus x. And we want to expand this function to n equal 4 with the center, the origin. Okay? Now, it might be very complicated to take the derivatives of this function, okay, for each order up to 4. So we may want to resort to the use of the theorem. So we'll first expand sine of x, and we know that this is x minus x to the cube divided by 3 factorial plus little o of x to the 4. In fact, we know that the term with x to the 4th is missing. And then we have that the logarithm of 1 plus x is equal to x minus x to the square divided by 2 plus x to the cube divided by 3 minus x to the 4 divided by 4 plus little o of x to the 4. Okay, so then we just need to multiply out. So we have f of x equal to x minus x to the cube divided by 3 factorial plus little o of x to the 4 times x minus x to the square divided by 2 plus x to the cube divided by 3 minus x to the 4 divided by 4 plus little o of x to the 4. All right. And then if we do the multiplication, we get, if we first multiply x, okay, we will go for multiplying this x but by all the other terms. Let's see what we get. We have x squared, right, minus x to the cube divided by 2. Then we have plus x to the 4 divided by 3 right? And of course the next term is going to be minus x to the 5 will be eaten by little o of x to the 4, so we can just neglect that. And the next one is going to be minus x to the 4 divided by 3 factorial, which is basically 6, right? And we can stop at this point because all the other terms are little o of x to the 4, right? So we can now rewrite this as x squared minus x to the cube divided by 2, because we have 1/3 minus 1/6, they both multiply x to the 4. We just have plus x to the 4 divided by 6 plus little o of x to the 4. So this is a much easier way of computing the Taylor polynomial for this product function. But this is not the only use that we can make of this. Suppose, for example, that you would like to know what is the derivative of order 4 evaluated at 0. Okay, again, if you go in the just along the way of taking the derivative, it might be a very long way, and it is also very easy to make mistakes. Instead, we could say something else. Okay, let's say that we want to find this. Well, what we know from the Taylor expansions, we know that from the Taylor expansion centered at 0, the coefficient of the x to the 4 will be fourth derivative evaluated at 0 divided by 4 factorial, okay? And these another useful properties we want to discuss here is the composition, okay? Composition. How can we expand the composition of functions? There will be two cases that we will consider. Let's suppose, for example, that we have f of x equal to Pn of x plus little o of x to the n, right? And we want to replace x with a multiple ax, where a is any real number. As always, let's exclude the origin, because otherwise it will become trivial. So it turns out that f of ax is what we get if we just replace the argument of the function with ax, and this will be Pn of ax plus little o of what? Well, little o of ax all raised to the n. But this is just like fax equal to Pn of ax, and because ax raised to the n is equal to an times x to the n, well, this is simply equal to little o of x to the n. So this is the thing to remember. Okay, so this is the expression we need to remember. And proving that little o of ax all raised to the n is just a little o of x to the n is very trivial. I will leave this as an exercise. Second composition is the following. As always, we have f of x equal to Pn of x plus little o of x to the n. We have a, which is a real number without the origin. Then if we replace x with x to the a, so f of x to the a, well, this is Pn of x to the a, right, plus little o of what? Of x to the a all raised to the n. All right, but this, again, this is simply f of x to the a Let's consider this example. F of x equal to e raised to the x squared times the cosine of 3x. And we want to expand this up to n equal 4 for x not equal to 0. Okay, we can use the expansion of et, right, the simple exponential, and we know that this will be 1 plus t plus 1/2 t squared plus 1 divided by 3 factorial t to the cube plus 1 divided by 4 factorial t to the fourth plus little o of t to the fourth. Of course, we are expanding this up to n equal 4. Let's see what happens if we replace t with x squared now. This is just, you see, the composition 2 that we are using. So we can rewrite that e to the x squared, because of what we know, we just need to replace t with x squared. Okay, so, and we get 1 plus x squared plus 1/2 x to the fourth. So we realize that this is the place where to stop, because every other term will have a power of x which is larger than 4. So we can just write little o of x to the 4. Let's see what happens with the cosine. Okay, so we know that the cosine of t is 1 minus t squared divided by 2 factorial plus t to the 4 divided by 4 factorial, but 4 factorial is simply 24. We can just write 24 plus little o of t to the 4. And now, by using the composition 1, we can write that the cosine of 3x, we just need to replace t with 3x, and we get 1 minus 9x squared divided by 2. Let me put the x squared here. Plus, we have 3 to the 4, and we have x to the 4 divided by, basically, 24 is nothing else that 3 times 8, okay, plus little o of x to the 4. So we can easily rewrite this as 1 minus 9/2 x squared. By just simplifying 1/3, we get 27 divided by 8 x to the 4 plus little o of x to the 4. Okay, so we are ready now to multiply out the two polynomials, because we know that f of x, f of x will be, at this point, the product of 1 plus x squared plus 1/2 x to the 4 plus little o of x to the 4 times 1 minus 9/2 x squared plus 27 divided by 8 x to the 4 plus little o of x to the 4. Alright, good. So let's multiply this out. We first multiply the 1 from the first term, so we get exactly the second factor, 1 minus 9/2 x squared plus 27 divided by 8 x to the 4 plus little o of x to the 4. Then we pass to x squared from the first term, so we get plus x squared minus 9/2 x to the 4, and of course we stop with x squared, but we have still another 1/2 x to the 4 plus little o of x to the 4. And now we can put together the terms with the x squared. We see that we have this term with x squared and this term with x squared, and instead we have also this term with x to the 4, this term with x to the 4 and this term with x to the 4, and if we do this multiplication we can easily find that this is 1 minus 7 half x squared plus, or let's consider now another example of composition. For example, f of x equal to sine of x to the fifth, and we want to have an expansion up to n equal 15 around the origin. Now, if we resort to the composition theorem, the first thing we need to do is expand the sine of t, which we know is t minus t to the cube divided by 3 factorial, and we know that when we will replace t with the x to the fifth, we are already at x to the 15, so we can stop just here and write little o of t to the cube. And of course this gives sine of x to the 5 equal to x to the 5 minus x to the 15 divided by 3 factorial plus little o of x to the 15. Okay, and this is done. Let's see what happens if we had expanded the sine of t, of course always stopping at t to the cube divided by 3 factorial, but because we know the sine of t is an odd function, we could also have little o of t to the 4, right? So this gives the expansion sine of x to the 5 equal to x to the 5 minus x to the 15 divided by 3 factorial plus little o of x to the 20, right? However, we know that because the next possible power would be 5, okay, so we know that the next power, the next, sorry, let me write, we know that the next term would be x to the 25. Why is that? Well, because the next term in the sine of t would be t to the 5, and when we replace x to the 5 in t to the 5, what we get is x to the 25. So we could also write this as x, we can write little o of x raised to 24.99. See? Okay, this is just a side notice, not very important. Now, we would like to use this expansion also to solve a similar problem about the derivative. Okay, so let's say that we would like to find the derivative of order 2016 in 0, and f of order 2015 in 0. Okay, we would like to find these two. Of course, forget about evaluating the first 2015 derivatives. Okay, this is crazy. One thing we can immediately say, right? We can immediately say that the derivative of order 2016 evaluated at 0 is 0, because sine of t is an odd function, right? So, I mean, clearly it will contain only odd terms, and if we multiply an odd term, um, whatever that is, the exponent of t, and we replace x to the 5, we always get an odd term. So the only possibility would be, of course, to get all the terms, derivatives of even order, to be equal to 0. But how about the derivative of order 2015? Okay, well, what we know is that this derivative in 0, of course, is the coefficient of x to the 2015, which is basically equal to t raised to the 2015 divided by 5, which is basically t to the 403. Okay, so we're saying that the sign of t will have an expansion, whatever, and at some point there will be a coefficient that will multiply t to the 403, and we know already what will be the denominator. The denominator is going to be 403 factorial. We know that there will be a 1 on top. The only thing that remains to be established is the sign of this. But we saw last time, when the studying and proving the expansion of the sign of t, we saw that the derivative of order 2k plus 1 in 0 is equal to 1 if k is even, and is equal to minus 1 if k is odd. Okay, so let's see. 403, well, this is basically 2 times 201, right, plus 1. So we see that in this case k is odd. So we can then find that this is indeed the sign. Okay, the coefficient of t raised to the 403 is minus 1 over 403 factorial, which implies that well, this implies that let me write down this below. So this implies that f, the derivative of order 2015 divided by 0 divided by 2015 factorial is equal to minus 1 over 403 factorial. And of course this gives that the derivative in 0 is just equal to minus 2015 factorial divided 403 factorial. As a final example of the application of the composition formula, let's solve the limit as x goes to 0 of this function, e to the 2x squared plus cosine of 2x minus 2 divided by x times arc tangent of x minus x. Okay, let's immediately check if this is one of the undeterminate forms. Well, at the numerator, if we just replace x equals 0, we have 1 plus 1 minus 2, so we get a 0. And also at the denominator we get a 0. So yes, this is an undeterminate formula. So we might want to just replace the function with their Taylor polynomials. Okay, the point is, what is the right order, okay, of the expansion? But if we look at the denominator, we immediately recognize that this if we attempt an expansion, okay, we attempt an expansion of the denominator, of course x will remain what it is. For the arctangent of x, we would replace x minus x to the cube divided by 3 factorial. There might be additional terms, okay, there might be additional terms, and then we have minus x. And because x and minus x will go away, we are left with a denominator that has order 4. So, I mean, we decide at this point to expand all the function up to n equal 4 around the origin. Okay, of course x naught is equal to 0. Why? Because we have that this limit is evaluated for x that tends to 0. Okay, so let's try this expansion. Okay, so we first start with e to the t, the exponential, and we have 1 plus t plus 1/2 t squared, and we realize that this is the point where to stop, because if we replace now t equal x squared, what we get? Well, we get e, actually we need to replace t with 2x, so we get e to the 2x equal to 1 plus 2x plus, then we have 1/2 of 2x to the square, which is 4 x to the 4th plus little o of x to the 4. Okay, so let me rewrite this as e to the sorry, I think we need to replace e to the 2x squared. Okay, so we have e to the 2x squared, and this is what in fact we get 4x to the 4th. So we can rewrite this as 2x to the square plus equal to 1 plus 2x squared plus what do we get? 2x to the 4 plus little o of x to the 4. So first function is done. And now let's go to the cosine. Well, the cosine of t, we know that this is given by 1 minus t squared divided by 2, and we have plus t to the 4 divided by 4 factorial plus little o t to the 4. Why we stopped at t to the 4? Because now we need to replace t with 2x. So what we get at this point is that the cosine of 2x is equal to 1 minus, we have 4x squared divided by 2 plus we get 16 x to the 4 divided by 24 plus little o x to the 4, and we can also rewrite this here, cosine of 2x equal to 1 minus, by just simplifying, we have minus 2x squared, and divided by 8 we get 2/3 x to the 4 plus little o of x to the 4. Okay. Finally, the arctangent of x. Well, we saw that this can be expanded up to x to the cube divided by 3, and of course this is little o of x to the 4 because the even powers are missing. Okay, so we are ready now to replace. Let me highlight what are the replacement that we need to do. We need to replace this formula, we need to replace this one, and we need to replace this one. Okay, so final expression becomes, well, instead of e to the 2x squared, we have, let me write 1 plus 2x squared plus 2x to the 4th plus little o of x to the 4th. Okay, so this is e to the 2x squared plus 1 minus 2x squared minus, sorry, we have plus 2/3 x to the 4 plus little o of x to the 4th minus 2, and at the denominator we have instead x squared minus 1/3 x to the 4th minus x squared plus little o of x to the 4th. Okay, so let's see if we can simplify something, and we can definitely simplify 1, 1 and minus 2, right? We can simplify 2x squared minus 2x squared, so that we are left with, we have 2x to the 4 plus 2/3 x to the 4, that gives at the numerator 1/3 x to the 4th, and we have only little o of x to the 4th. At the denominator instead, we can simplify x squared and minus x squared, so we're left with minus 1/3 x to the 4 plus little o of x to the 4, and clearly this is something that tends to minus 8. So we finally solved the limit by deciding what was the proper degree of expansion of all the functions present in the limit. In alternative, it is worth mentioning, we could have used the L'Hopital 4 times. Why 4 times? Because we know at this point that the limit needs at